Okay, I'll talk about some material from lecture 17. As always, this video, watching videos in general, is no substitute for reading the book and notes. All right, first thing I want to talk about is the cumulative probability distribution. The cumulative probability distribution, usually called the CDF. Let's suppose I have a random variable x, and for us, we're only really going to apply this to normal distributions, so we'll suppose that x is normally distributed with mean mu and standard deviation sigma. So the PDF of x looks like this. There you go. This, of course, would be mu, and so on. Well, the CDF of x is a function, that's a lowercase x. The CDF function at x is the probability that the random variable x is less than the value little x. So, for example, when the value little x is equal to mu, then the CDF of x should be equal to 1/2, because that's the probability that the random variable is less than mu. So if I were to graph the CDF of x, first of all, the maximum value would be 1, right? Because probabilities only go between 0 and 1. Out toward, minus infinity out here, let's just pick an x all the way out here. We'll call this one x1. x1, that might be x1 right there. What's the CDF, what's the y value on the graph of this thing when x is equal to x1? Well, it's the area to the left of this little x1 here, so it would be a very small number. Let's say this is x2. Now, what's the y value over here on the CDF? Well, it's going to be the area to the left of x2. At least that's a number you can kind of see. x2, so that maybe would be that. Right? We'll put x3 here. x3, well, now we're getting somewhere. This is more like a quarter, right? A big value. When we get up to mu, of course, we got to get to 1/2, because the area to the left of mu, the probability that x is less than mu, is 1/2. All right? And if we just keep going on, right, first of all, this thing keeps increasing because we're always adding more probability, more area, right? And it's going to look kind of like this. There are going to be values here, here, here. It's going to look like this. I didn't do a very good job of sketching it there, but that's the idea. The y value over here, if you have a point x comma y on the CDF, the graph of the CDF, then the y value is the area to the left of x under the PDF for that random variable x. Or, alternatively, it's the probability that random variable x is less than x. So when x is over to the left under the CDF, when x is over to the left, the y values are small because you haven't got much area to the left, right? They grow and grow. By the time you reach excuse me, the mean mu, right? The area to the left of mu is 1/2, so the y value here would be 1/2. Right? And as you go out to the right, the y values get closer and closer to 1. Excuse me. All right, let me do a little sort of problem about this. Okay, we're given an ogive, this word right here, it's pronounced ogive, and it means the graph of a cumulative distribution function. Okay. Given this ogive, what's Q3? Okay. Well, remember what Q3 means. That's a number on the x-axis so that 3/4 of the area under the PDF is to the left of Q3. what's on the y-axis here is areas under the PDF, basically. Right? So you need to find the x value over here somewhere so that the y value of the corresponding point on this thing is 0.75, 3/4. So what I'm going to say that's 79. I'm just estimating from a graph, so that's close enough. So this would say that when x is 79, y is 0.75. That is, when x about 3/4 of the area under the PDF, of which this is the CDF, about 3/4 of the area under the PDF is to the left of 79. So you would say that Q3 is about 79. What's P33? Well, you get it in much the same way. Right? P33 is a number on the x-axis, so that 33% of the area under the PDF is to the left of P33. So where's P33 going to be here? Well, the y value has to be 33. So it's going to be about right there. I'm going to guess that that's 72. So P33 would be about 72. Excuse me. Okay, we won't do a great deal with it. Here's the next little thing. I want to talk about the normal probability plot, or what's often called a QQ plot. Okay, the reason to even look at this thing is this. Many times you get data and you don't know much about the population that it was sampled from. For example, you don't know whether that population is approximately normally distributed or not. There are many techniques you can use only if the population is approximately normally distributed. And so you need some way to determine whether that's probably the case. Sometimes you can get an idea just from knowing where the data came from. You can expect that it will be approximately normally distributed. Excuse me. Sometimes you can just plot the data. There's some data, you got a bunch of sample data, you put it on a number line, there you go. And it looks kind of like that, right? Oh, I don't know. Well, maybe that's normally distributed. Right? It looks kind of thicker in the middle than it does at the ends, but is it really close to normally distributed? It's very hard to tell by just looking at dots on a line, unless it's really clear. Another way you could tell is by making histograms. Right? You could make histograms, let's say, well, we use bars this wide. You'd expect low bars here, slightly higher bars, and so on. It looks like that's happening. Then there's really low bars. Seems to be maybe an empty one, and then one like this. Well, is that data normally from a normally distributed population? Maybe. Most of the histogram looks good, but again, it's really hard to tell. And what's more, if I use different width bars, I'd get a different picture. So again, unless it's really clear that the data is normally distributed or is not, it's very hard to tell from this. The QQ plot is the solution to this, one possible solution. What it does is it takes data points like this and it turns them into a scatter plot. And so the scatter plot might look like this. And the thing about this, the kind of scatter plot it is, and we won't talk about the details of how to get this thing, but the thing about this scatter plot is that if the data were perfectly normally distributed, all those points would fall on a straight line. And the farther the data is from being normally distributed, the farther these points will be from being on a line. So what you do is you make the QQ plot and see if the points fall pretty close to a line. If they do, then you decide the data is probably from a normally distributed population. Right? And if they don't, you decide it probably wasn't. Of course, it takes practice to decide to be able to look at a plot and decide whether the population is probably normally distributed or not. And you'll never get that practice in this class. Here you just need to know a very basic thing about this. I want to show you an actual picture of one of these. This was made with the TI calculator. I got about, I don't know, maybe 30 data points over there. Yeah, it's 30. And here's the QQ plot that came from it. Right? Again, you will not need to know how to make these things. But is this data close enough to a straight line to decide that are these dots close enough to a straight line to decide that this data is probably from a normally distributed population? Oh, very much so. Right? We do seem to have one exception, but most of them fall really close to a straight line. And in fact, of course, I made this up, so I happen to know that that data was sampled from a normal distribution. Okay, pretty much the only thing you need to know about these normal probability plots, or QQ plots, for this class is that they are the answer to the question, what is the best way to decide whether sample data is from an approximately normally distributed population? The correct answer to that question is a QQ plot, or a normal probability plot. All right. Here's another little topic. You remember that when I was talking about binomial distribution, I gave you the mean and standard deviation of a binomial distribution and said we'd use it later? Well, the time has come. You remember that for the binomial distribution B of NP, meaning you have n trials and the probability of success on any one trial is P. Right? For that distribution, the mean was n times P, and the standard deviation was the square root of n times P times Q. You remember, of course, that Q is just 1 minus P. Right? Well, it turns out that binomial distributions can be pretty well approximated by normal distributions in many cases, and it's not uncommon to do it. Right? In fact, any time you have NP greater than 5 and NQ greater than 5, right? That's the criterion for when you can approximate a binomial by a normal distribution. Anytime this is the case, right, this binomial distribution here for n trials and probability of success P on any one trial is going to be approximately the same as the normal distribution with mean NP and standard deviation the square root of NPQ. Okay. There are some details here, and I'll show you one in an example. You won't actually have to work problems involving this, at least not very many. What you will need to do is be able to say what the correct normal distribution is to use to approximate a given binomial distribution. Okay, let me show you an example of using this. So, when a healthy adult is given cholera vaccine, the probability that he will contract cholera if exposed is known to be 0.15. 500 vaccinated tourists, all healthy adults, were exposed while on a cruise. What is the probability that more than 75 will contract the disease? So this is pretty clearly binomial. Right? We have n equal 500. We think of testing each tourist and seeing whether the test comes out infected or not infected. And we know that the probability of success, we're going to call it success, is 0.15. I mean, writing that means that success is infected, even though that's a pretty funny thing to consider success. In this case, x, remember the random variable x counts the number of successes, so x counts the number infected. And we're asked, what's the probability that x is greater than 75? Well, we can do this directly with binomial CDF, right? we know how to find the probability for a binomial random variable. We know how to find the probability that that there are at more than 75 successes. Right? We would have to compute 1 minus binom CDF of, right, what are the arguments? NPX. Right? So we would have 500.15, and we're asked for the probability x is greater than 75, so that would be 76 or more, meaning that we'd have to use 75 here. And that turns out to be, I have the approximation here, it's about 0.469. Okay. When we're using normal CDF, when we use a normal approximation, we don't compute the probability that x is greater than 75 because we've switched. Here's a picture of the two distributions, and you can see they're really close. Right? We're not computing the probability that x is greater than 75. What's normal to do, what's the usual thing to do, is to use 75.5. That is to compute the probability that x is greater than 75.5 when we're trying to approximate the probability that more than 75 people end up with cholera. So the approximation we would use would be x is greater than 75.5, which of course would be normal CDF of 75.5 to the TI calculator infinity with mean, well, what are the mean and standard deviation? Oh, let's go over here and figure them out. So the mean, right, NP is 500 times 0.15, that's 75. The standard deviation, that would be the square root of NPQ, and that turns out, well, that's the square root of 500 times 0.15 times 1 minus 0.15. That turns out to be, let's see, 7.9843. Close enough. So when you go to put this stuff in normal CDF, you would put in 75 for the mean, and this number, 7.9843 for the standard deviation. And you end up with 0.475 for the probability. Well, that's pretty close. It's certainly close enough if you were, say, a ship's doctor, you might, considering how many doses of medication to stock in your medical storage, this would be plenty close enough to give you an idea. All right, one more little thing, and this is not something you'll be tested on at all. This is just a rule of thumb that people who work with this stuff know and use. Suppose you have some data that's approximately normally distributed. The data is approximately normally distributed. Okay, take a look at this. The empirical rule says that 95% of that data will be within 2 standard deviations of the mean, so between this point and this point. In practice, it's often more than 95%, but you know it's going to be at least 95%. And that says that this interval here, which is 4 standard deviations wide, let's call it 4 sigma. Right? It shouldn't really be 4 sigma. Let's call it 4s. Right? 4s contains almost all the data. Right? An interval of that width contains almost all the data. So that's going to be pretty close to the range of the data, from the smallest to the largest point. Now that's not the way this is used. The way this is used is that means that the standard deviation of this stuff is approximately the range over 4. And that's really the rule of thumb. If you have data and you have reason to think it's probably close to normally distributed, then you can use the approximation standard deviation is about range over 4, just to get an idea, maybe in your head, of some stuff about the data, how it's distributed. All right, that's it for this lecture.